all the lectures of this conference are being recorded, and as a matter of fact, they are being broadcasted live on the YouTube channel, youtube.com/IMPABR. And then you have the IMPA video site as well, the video.impa.br. So all the lectures will be there right after the end of the day and broadcasted live. So if you know of any students or your postdocs or any of your colleagues that could not be here and you want them to see some of the lectures, you can just forward them the link. And by the way, I should have asked for all the permissions of the speakers to actually record you, right? But if anyone has any objection, please let us know and we'll gladly withdraw your lecture from the website, okay? So this is assuming under the premise that everything is okay with the dissemination of the information. Okay, so let's continue with our program for this afternoon. It's my great pleasure to introduce my senior colleague, Felipe Linares from IMPA. Felipe works in the dispersive equations. He got his PhD from Penn State, right, Felipe, in 1992, under the direction of Gustavo Ponce and Jerry Bona. And he wrote later on with Gustavo Ponce a very nice book, The Introduction to Nonlinear Dispersive Equations. And Felipe is one of the responsible for the dissemination of the field of dispersive equations and harmonic analysis here in Brazil. It's a great pleasure to have you here, Felipe. He'll be talking about propagation of regularity of solutions to the K-generalized Korteweg-de Vries equation.
Okay, thank you, Emmanuel, for the introduction. And thank you for the organizer to invite me to share with you this topic that is a little bit far from the main stream. But anyway, I'm going to talk about this regularity propagation of solutions. I say for generalized KdV equation. Actually, I'm going to focus in KdV, right? So I'm going to write here it's only KdV. Probably in some moment, I'm going to mention something for the modified KdV equation. Okay, so I'm going to focus on that equation. And I had to tell you that what I'm going to show today is a series of work in collaboration with Gustavo Ponce from University of California, Pedro Izaza from the Universidad Nacional de Colombia in Medellín, and Derek Smith from University of California, Santa Barbara, too. Okay, so the idea of the talk is the following. I'm going to give a motivation. Then I'm going to talk about the propagation of regularity for the KdV equation. And then I'm going to give a very short idea of the proof, some remarks, then extension of that result. And then I'm going to tell you something that we got recently. It's a different kind of propagation. Okay? So let's begin with this very simple linear problem, right? So you have the linear problem associated to the KdV equation, right? So you begin with the data in HS, and then you can solve this problem just using the Fourier transform, and that defines the unitary group associated to that equation. And we can see that if you begin with initial data in HS, so because of this property, you stay there, right? And moreover, if you have initial data in HS only, but no in HS prime, then you have this property, okay? So there is no propagation of regularity in that sense. Now you move to the nonlinear problem, right? So you have the initial value problem here, now associated to the KdV, right? And then you know, well, we know that this is locally well posed, globally well posed, for any s greater or equal than 3/4. Okay, 3/4 could be global, local, whatever. But we are just interested in the local well posedness to produce our results here. Okay, so for this case, in the nonlinear case, you can begin with initial data, right, in HS prime, but initial data in that is no NHS double prime with this relation, and then you preserve the same property that you have in the linear case. Okay? So there is, you begin in HS, you stay in HS. Then we can look more closely to the solution of the linear problem, right? So if you look at the linear problem again, right? So you can write it explicitly in this form. You have a convolution between this function that is called the area function. This is a oscillatory integral, and it has a very nice behavior, right? So it oscillates in one side and then decay exponentially with this decay here. Okay, so we're going to look this number again along the top. Okay, so you can show that solution of that linear problem satisfies what is called the Stricker estimate. Okay, so you got solution of the linear problem associated to the KDB, and then you see that if you begin in L2, then the solution is more regular, right, in this norm, right, than the initial data. Okay, so in particular, you can have this result. You have a gain of 1/4 derivative in this norm, and if you don't have derivative, still you are in a better space. Okay, this result was established by Kenny, Ponce, and Vega in the last century, right? And then we have, let me say something about this before going up. And you may ask why you gain this derivative and what is the reason to have no derivative here, right? So what is behind the whole thing is that you have to look at the symbol associated to the linear problem, right? And then you have to look for the curvature of the symbol, the associated symbol, right? For instance, in the Schrödinger case, the curvature is constant, so you don't gain any derivative. Here, we are putting something like it's the second derivative of the symbol, right? And then you have this gain of derivative over there. Okay, so now we move a little bit and we try to explain what is the Kato smoothing effect. That is a key ingredient to get resolved below H1 to obtain the local well-postness for the IBP associated to the KDB equation. Okay, so you begin with that equation here, right? And then you multiply that equation by this, where chi is a infinitive function, increasing positive with derivative with compact support, and that thing positive, right? Then you multiply, and then you integrate in x, and do some integration by parts, right? So what you notice is that, well, you want to control this guy over here, right? So you can control it using this quantity here, and then because this guy is positive, you can use an interpolation between L2 and derivative in L2, right? So what you come out with that is that the solution with the initial data in L2, that remains in L2, and then you have a gain of derivative in this interval, in this square over here. Of course, this quantity, this computation here was done by Toshio Kato in 1983, and at the time, the local well-postness known, it was S greater than 3/2. Okay, but with the technology after that, you can actually have the result in L2, and still you have this gain of derivative over there. So this result was extended, this smoothing effect by Constantin and Sot. They were looking at it behind that property for PDEs, right? And the same result was obtained by Jolin and Vega, and they were looking for a different kind of problem posed by Carlenson on pointwise convergence, right, for solution of the Schrodinger equation. Okay, so Kenny-Ponce-Vega proved something stronger that Cato did. So they have the smoothing effect, and now you can notice that you have first an integration in T, right, for any x in the real line, right? So this is what is called the homogeneous smoothing effect. So we are thinking on this solution of this problem over here. So you have only the homogeneous problem. And then for solution of that problem, you can obtain a gain of one derivative in some norm that is L infinity in x, L2 in t, right? But if you consider this no homogeneous problem, then homogeneous problem, you put in there G, x and t, and this equal to 0, you can obtain a gain of two derivatives. Okay, so you have two derivatives in that norm, right? Is controlled by this, right? So you can use this kind of estimates to prove for, well, I'm going to show some result in the front, and we are going to use this in order to get the local well-postness in some weighted Sobolev spaces. Okay, so now suppose that instead to have the chi function only depending on x, that depends on x and t, right? So look at the linear problem only without g. Then you do exactly the same. You multiply it by u times chi. And then this derivative is going to appear there, right? And you want to maintain the information that you have before, right? So in order to do that, you have to kill these two guys over there, for instance. And then you choose something that looks like this, right? So if you do the computation, roughly speaking here, you can obtain alpha equal 3/2 and a function of time like this, okay? So you have a weight over there with this phase. Well, actually, you can prove something more interesting than that, and it's the following. If you begin with initial data in L2, right, with that exponential decay, right, you remain in that space, all right? And then you have, again, this is the function exactly. I consider now the nonlinear problem, and you got exactly this. And this problem is this result is sharp in the following sense. So Escuriaza, Kenny, Ponce, and Vega in 2006, they were working on this unique continuation principle for some dispersive equations, right? So in particular, if you choose a function here in that space, then assuming that you have this decay, right, in two different times, then they show that that is identically equal to 0, right? So what the result that we showed before, is something that says I have two different times, right? Here. So I cannot go from time t0 to time t1 if with the same decay, right? Otherwise, I have to be equal to 0. I can go from t0 to t1 with this, right? So this is deteriorated, right? Okay, that is in the sense that this is sharp. Okay, now let's begin with the main topic of the talk. And this is the propagation of regularity, and this is in the following sense. We begin with data in H3/4 plus, and suppose that you have the restriction of this data here in this half line is of this order, right? It's an HL, L integer, right? Be a positive number or any real number. Then what we show is that the corresponding solution is over there, okay, for any beta and any time 0, between 0 and t. Okay, so you begin with some regularity in the data, right, from x naught, right? And then you have the regularity for the solution in the same space. Okay, so I'm going to be more explicit. And before describe the main result, we need to have a local well-posted result. And this is the one by Kenny, Ponce, and Vega, again from the last century. And you begin with data in this space. Then you use the Stricker estimate. You use the smoothing effect. And then you use the maximal function estimate. Then you will have local well-postedness here. Okay, and this is a persistent property too, right? Okay, so we have that data and with information, and this is the result that we proved with Pedro Izaza and Gustavo Ponce, and it just appeared this year. So you have initial data in 3/4 plus, right? And suppose that you have this property here, then the solution satisfies this, okay? With some constant that depend on the initial data and the derivative in the half line, right? So you can see that you are in that space, and this side is moving, right? So it's moving to the left. So moreover, you can have one more derivative that the smoothing effect of cathode type is also preserved in this interval of time, this interval of x, right? So what you say is, I begin here, and then I'm moving, right, in this side, and you're getting more regular in the left-hand side. This is what the theorem says. So you can see that you have this result here. You can ask also for integrability if you want, right? You have in L2, but then you want some more information about that. Actually, you can prove this, right? So exactly. You have the gain of regularity, you have to pay with some weight, right? And then you will have this result and the decay in terms of time. That was a question that was asked to us from Kenji Nakanishi. Okay, so also one thing that is a general rule in dispersive equation is that if you have some decay, you gain regularity, okay? So we look at this problem, right? You begin with some decay, begin with Izaza Ponce. In one side, beginning with a regularity that is 3/4 plus, and then you assume that it happens, then you can prove that you still satisfy this condition. Okay, so the flow satisfies this property. And moreover, you gain some regularity, right? Out of 0, so you gain the regularity with some weight, and a regularity +1 with this weight. All right? Okay, so, okay, let me keep going. So in particular, we can deduce from those results the following corollary. So suppose you begin again, with the same solution in 3/4, right? And suppose that you have the derivative of order m in some time t hat that is known in L2. So what can you say about the solution? So what you can say that in the past, the solution was no better than now. Okay, so if this is bad now, it's because it was bad before. Okay, so there is no regularity before, there is no decay before. All right, this is what we can deduce from the main result. Okay, so we are saying something that you have regularity on the right-hand side, and then the regularity propagates on the left-hand side, right? So that means you have infinite speed of propagation to the left, and then singularity should travel to the left, right? So it has to do something with this resolution and conjecture somehow, right? And the resolution conjecture is basically like if you are in this kind of dispersive equation, particular for the Schrödinger equation, what the conjecture said is that the solutions eventually resolve the equation in a superposition of solution of the linear problem plus some ground state, nonlinear ground states. Okay? This is the resolution conjecture. So this result may think you about that, but it's not quite. Okay, I'm going to tell you something about that in a few minutes. Okay. So there is another result in the same direction that says the following. You begin in this class, right? Before I mentioned a result, assuming that I was in some space like this. Actually, we prove, Sasa Ponce and myself, that if you begin in this space, you remain in that space, and that is a if and only if condition. And what is behind that is the following. You have two operators over there. This is the linear operator associated to the KDB, the linear part. And this operator here, this is, I'm going to put this like this, 3t second derivative on x. So what you can see is that here, if you want to have a weight of order 1, right, you have to pay with two derivatives of regularity, right? And this is what say here, right? So you have regularity has to be twice the decay. Right? And we prove that this is not only sufficient, but a necessary condition to remain in that space. Now, what we see is that, again, you have two different times, T0, T1, and suppose you have decay in here is T1, you have a decay here, right? And you have that decay over here. And what happened is that the solution is smooth. Okay, so you can glue the information that you have in one side and another side, and then you put it together, right? So you have a solution that it has to be in this space, okay, with this information over there. Okay, so I just want to show you a couple of slides with the proof. Well, again, what we follow is energy estimate, like Cato did, with weights. Okay, so we have to choose the right weight. So we construct a weight, satisfying these conditions over here, right? So exactly like Cato You begin with you have a infinity function. You have the first derivative has to be positive, and then the asymptotic behavior has to be like this, and then you have some properties in the middle just to control some terms. And then what you do is exactly what I did before to show cathode smoothing effect. So you have energy estimates. So you want to control, you begin with a data in H3, 4 plus, right? And now you want to have the information of one derivative. So you have one derivative here. Then this is a new term that appears. Then you have a second derivative here that you may say, well, you are getting in trouble. Then you have first derivative like here. And then you have the nonlinear term, right? So if we remember the cathode smoothing effect, we are fine in this side, okay? Because I gain one derivative over there. So I have this condition. Here is no problem. You have this is positive. Somehow we can absorb that with this, right? And this is okay too. And if you develop this derivative, you may have some problems. Okay, so you will have one derivative here, one derivative here, and one derivative here. So I have the right to put only two derivatives in L2. And what about this one? I cannot use the embedding, right? The Sobolev embedding. So I use streakers. Because I have a 3/4 derivative, I can control one derivative. All right? So this is the game that we play. All right, now, what is the meaning of singularity of the solution travels to the left? Okay, so is that clear that that happens? Well, now we look at this initial value problem associated to the modified KDB equation. This is also an integrable system as KDB. And then let's see what happens. So we can follow the argument of Jerry Bonan and Jean-Claude So, where they show that if you begin with initial data in H1, and it's also infinity, then what you can prove is that you have the solution is C1, right, out of the integers, and is not in the integers. Okay, so you have some singularities, right, in the integers, right? So that's is in contrast with this phenomenon that I said before, right? You have a singularity, and you keep that singularity in several moments, right? So you can prove that the following, like Jerry Bonan and Jean-Claude So, they use the asymptotic decay explicitly what the area function is, right? And then they construct the solution, the initial value data, or the initial data that make possible these singularities on time. So what I did a long time ago with Marcia was simplify that proof, and we just use the fact that, at least for modified KDB and above, when you write this problem, you can write it in the integral form like this. So you have this, and then you have the nonlinear part written as this, right? So what we did was to show that if you begin when a data in H1, then this guy here belongs to this space. Okay? So you get for free that part is C1, right? So the problem reduced to the linear problem. Okay, the linear solution. Okay, the whole thing is there. So we can adapt that proof to do this here. well, we can say something more. So now, suppose that you begin in this space, a solvable space, now with base P, right, LP. So you begin with P greater than 2, and initial data over here. Then we have a solution. Again, it's a nice solution over here. And then we can prove that there exists a time t where this solution is not anymore in that space. Okay? So we can follow exactly the proof if k greater or equal than 2, like we did for modified KDB. And, well, what we can do, what we can say more, is this. You have now the solution, the data in R minus, right? So what happened with the regularities? They don't propagate forward or backward in time to the right or to the left. Okay, so there is no propagation at all in those spaces. All right? Okay, so this is singularity travel to the left. I have to be careful. We have to be careful with that. Okay, so we also, I say, Isasa, Ponce, and myself, we work with these two equations, the initial value problem associated to the Benjamin-Ono equation and the KP2 equation. And we prove the same kind of regularity, right? So you move to the left. So you begin with a regularity on the right, and then it travels to the left. And we have to observe here that, again, you use the smoothing effect of Kato type. And for this guy here, you only gain half derivative. So you have to do it twice. Okay? For this one, you travel only in x. Okay, the propagation in x. And then you have a gain of exactly one derivative on the left, right? On the x factor. Okay, so the KDB, Benjamin-Ono, and KP2, they are integrable systems, right? And you may think about and say, well, this property has to be for integrable system, right? This is true. Well, at least if you look at this, what is K generalized dispersive Benjamin-Ono equation, okay, you have a different symbol here with alpha equal to 1 correspond to the Benjamin-Ono, and alpha equal to 2 depends on, it's exactly the KDB equation. And we know how to prove it in the extremes, right, in 1 and 2. But we don't know what is going on in the middle, right? So in that point, I say, well, if you know how to obtain a smoothing effect of Kato type, right, I'm going to have it using like a Kenny-Ponce and Vega approach, right? This is a general theorem. But doing by integration by parts is not clear. Okay, so again, so you say, well, this is a property that maybe is more general than only for this integral system, right? And then you keep going and look at this more general, this general quasi-linear equation of KDB type. So you have now something coefficient with some particular properties here, right? And B also has some properties over there. And then what happens is that you can also prove the propagation of regularity like for the generalized KDB equation. Okay? For that, you need to know this here. So you have this result by Craig, Capellera, and Strauss. It's about 2000, before 2000. And what they prove is the following. beginning with this m, there is no better m, right? N greater or equal than 7. Then you have a solution, right? This is a unique solution, but and then you have the smoothing effect of Kato type 2, but you don't have continuous dependence on the data. Okay, so you have only existence and uniqueness for the quasi-linear system that I showed before. So we need to have a refinement of that in order to justify what we did before. So in this energy-weighted estimate, we use strongly the continuous dependence, right, to justify the computations in the middle. So we prove, this is now with Gustavo and Derek Smith, a student in California, the following refinement of the result. So you have a beginning again. 7 is the best you can obtain. And then you have a solution that is almost when we want, right? It's continuous in M, and we are missing just a point, a little bit, with this Kato smoothing effect. But then we have that the map data solution is locally continuous from that space to that space over here. So we can justify the computation. So the result is this one over here. So you begin with initial data in HM greater or equal than 7. And now you have n still larger than m, right, with these derivatives over there. Then you can show that you can control all these derivatives above m, right, moving again to the left, right? So this is a propagation phenomenon still satisfied for this general quasi-linear system. And what we conjecture on the whole stuff there is that probably what is going on behind is that you have the Kato smoothing effect. If you can do it by integration by parts, then you can obtain this propagation of regularity to the left, right? All right, so let's move it a little bit. And now I just want to show you that we, again, with some dispersive equations, or almost a different kind of dispersive equations, but very, very similar to the previous one, you have a different kind of propagation of regularity. So this model over here is called the Benjamin-Bona-Mahoney equation, and basically was derived to justify what the KDB can be modeled, right? So it was easy to work with BBM that worked with KDB. I'm telling that in 1975 or whatever, right? So for that equation, we know that we have this local result and global one. This is local in L2, is global in H1. By Jerry Bona and Nikolai Setkov. So they prove that if you begin initially with a data in HS, s greater or equal than 0, you stay there, right? And then the map data solution is locally continuous in HS. So what we prove is that if you begin with data in HS, s greater or equal than 0, and then if you have a open set in R with the initial data satisfying that this is CK plus theta, then the corresponding solution satisfies exactly the same. Okay, so it's no better, it's no worse, it's just like that. Okay, so even though it's an approximation for KDB equation, it doesn't have the same structure in that sense, no? The regularity or whatever. So you can say something more, right? So you begin with the initial data, is this interval AB, right? And you know that this is in A x naught b is ck plus theta, and is not in the whole interval, right? The same happens to the solution. Okay, so it's no better, it's no worse on time. Okay, so finally, no, this is two more to go. So it's, you can see this is completely different what happened to the KDB and the other models. And you can also extend that kind of different regularity to models like this. The Gasper processes equation that is very close to Kamasa-Hall. But for Kamasa-Hall is open. We don't know how to do it. And this kind of it's a porous median model, and the 1D case, this is like this. Okay, so, and to prove this result, we have to use some basic PDE, this characteristic equation, characteristic method, and so. Okay, so this is all, and thank you very much for your attention.
Any questions or comments for Felipe?